Hello, this is Dr. Arterberg, and our presentation today regarding logic in mechatronics. The topics will follow the reference textbook by Bolton. We'll talk about logic, gates, applications, and data presentation, displays, recording, measurement, testing, and calibration. The logic gate that we'll start with is the AND gate. It is designated as shown over here with two inputs, X and Y, and the output is Z. The truth table is shown over here. Only when X and Y are 1, the Z is 1. Any other combination, the Z is 0. We see that when X and Y are 1, Z is 1. Any other combination, 0 and 1, 1 and 0, 0 and 0, Z is 0. We see the configuration of the circuit over here. We have the X and Y coming in through a resistor into the amplifier, into the transistor. We have a 5-volt DC that can only be transferred to the ground if both X and Y are active. So if either one of them is not active, the transistor is going to be disconnected, short-circuited, and there is not going to be any current flowing into this transistor, which will set up Z to high. The next gate is OR. We see over here two diodes, and in order for the output to go through the Z and down to ground through the resistor, either one of these diodes has to conduct the current. We see the designation over here, and the truth table is shown over here that we get 1 when either one of them or both are 1. And the only way we get 0 at Z is when both of them are 0. We're showing over here other types of common gates. We have here the NOT, which is just a triangle with a circle. So this means that if this is 1, this will be 0, and vice versa. We see the NAND, which has a dot at the end of the end. This is exactly the opposite of the AND. This is the NOR, exactly the inverse of the OR. We also have exclusive OR, which is similar to the OR with one exception, that at the OR we have the output showing 1 and 1 when either one or both is 1. But with XOR, the only way we get 1 at the output is only if one of them is 1. If both of them are 1, the output is 0. And similarly, we have the XNOR, which is exclusive NOR. We see here an example of a comparator. Suppose that we have 2 3 bits that we like to compare them. Bit 1 coming in from a cable, and bit 1 for B coming in from the second cable. And the only way that we could get a positive output at F is if both A3 and B3 are equal to each other. A2 and B2 are equal to each other, and A1 and B1 equal to each other. So these are XNORs according to the designation. And the only way that there can be an output here is if both the inputs are 1. Every other combination will give it a 0. So when all these couples are equal to each other, we will have an output on each one of them. And this is going to set the output over here. So to 1 only if this one and this one and this one are equal to 1. We see here an example of a flip-flop commonly used in electronic circuits. We have 2 NOR gates, and they are intercoupled. We have a reset coming in here to the first gate, and we have a feedback from the second gate coming in into the first one. And similarly, a feedback from the output of the first one is feeding into the second one. So what we have here is a case where we would like to set the flip-flop such that there will be an output 1. And then no matter what happens to the set later, output is going to be memorized until the reset is being set. And when the reset is going to be on, then no matter what else is going to be done to the reset, it's not going to change the output unless it's set. So that's flipping between the two of them. Let's see how it works. If the reset is 0 and set is equal to 1, then what we have here at the NOR, we have 1, therefore any 1 will give us 0. 0 will input into the first one, and then when we have 0 and 0 on both of them, then the output is 1, which feeds back here, and then 1 and 1 also give us 0. So this is the first condition, when S set to 1. Now when S set to 0, we still have a 0. We haven't changed anything, and 1 is still here. The only thing is 1 and 0 is still 0 here, and everything else stays the same. But when the reset is set to 1, and the set is still 0, then when we have 1 and 1 over here, this becomes 0. 0 feeds in. 0 and 0 becomes 1. So this is stable. And then if we change the reset to 0 again, nothing is changed. So that's the circuit diagram for the flip-flop. We can use flip-flops in registers. Registers are groups of flip-flops that memorize until they reset the input data. We see over here, for example, a 4-bit parallel data coming in, and it's being reset with a clock. And over here we have flip-flop A, B, C, and D, and every time a clock is resetting it, then the parallel data output goes down to the another set of manipulation, public computation. And then we have a similar example where we have the same 4-bit coming in, and then the flip-flop with slightly different configuration is converting it to from parallel data to serial data. Every time the clock will bit when it's reset, then the information from this one will go down the road, and then from this flip-flop it comes into here, and this data is going to flow serially. We see here an example of a timer. This particular timer is called 555 timer because it includes in it 3 5K resistors. And we can see how this may be used as an alarm system. We have over here a sensor and another sensor, 2 sensors. Each of them is set to a certain alarming reference. And we have reference over here and reference over here. This is a comparator that once the sensor data over here is exceeding the reference, it's going to be an output 1 here. And similarly here, when both of these outputs are 1, this is an AND gate, then we're going to have an input here to OR when either the feedback that we come here is 1 or this input is 1. Then what we do is we trigger the timer. And the way the timer is being triggered, as soon as the trigger sets an output 1 here, so this is going to continue the process. This is a set. The trigger, which normally ground the voltage across the capacitor, is now going to cut it off, and the voltage, which is going to be set here by a master switch into the capacitor, is going to let the capacitor start charging. And then when the capacitor gets to, after a certain time, which is determined by the resistance and the capacitance, the time constant of this combination is R times C, R in ohm, C in farads. The result is in seconds. Then what we have is the voltage is going to build up until we hit the threshold. And then when the output here was 1, the coil could set up an alarm. But then when the threshold is hit, then the output now is back to 0. The alarm shuts off and we reset the system. So here's an example how we use the timer into an alarm system. We have to be careful when we use the sensing devices with some other external devices, such as measuring devices, to make sure that we are not overloading the sensor. And each of the measuring devices has an input and output impedance. Impedance is the effective resistance that the electric circuit is exerting on the input to the system. And it is combined of a resistance and reactance. And the reactance is the non-resistive component of the impedance, which depends on the frequency. For example, resistance does not depend on frequency, but the capacitor resistance would depend on the frequency, the reactance, and so is the inductor. We see, for example, over here, that as the frequency tends to be 0, this is an isolator. The resistance is infinite. But when the frequency is very high, the resistance to flow is becoming low according to this equation. The reactance equals 1 over 2 pi frequency and the capacitance. Now, how does it play in loading? We see over here that we have a sensor with a voltage source, and we have over here a measuring device with a loading source. Now, in order for the loading velocity, input voltage into the measuring device, which we want it to be exactly as the sensing device, we must have the input resistance over here of the load to be very, very high. Otherwise, can't we flow here and will take away some of the voltage. There will be voltage to updo it. And at the same time, we want to make sure that the voltage source resistance is very low. So the impedance of the input impedance of the load has to be very high, and the output impedance has to be very low. So what we see here is an example of a sensing device which has its impedance. This is its output impedance. And we have over here a measuring device with its input impedance. We like to have the output at the measuring device be equal to the output of the sensing device. So we measure exactly what we sense. And if we look at the configuration here, we see two resistors, which are over here. They are connected together, and this is like a voltage divider, where the voltage here equals to the voltage at the sensing device times the resistance of the measuring device divided by the summation of these two resistances. And if we change the terms over here, we see that the voltage at the measuring device equal to the output divided by 1 plus this ratio. So in order for V in to be equal to VO, then RO has to be small and RI has to be large. The displays could take various forms, and as the textbook show us. And what we'll take a look is a few of them. Magnetic recording, for example, is based on a device that we have a disk in motion. We have a read-guide head, and then what happens is we charge the charger, the head, in one direction. Then we align the random media particles in a certain direction, and then they will be aligned in the other direction when we charge it in a different direction. And this is magnetized and memorized, and then when we play it, we basically getting the signal back at the read head, and can translate that to digital signals. We have over here an optical recording system. The optical recording system receives an input from a device, and then we have a laser which is connected to the read head, and we have a focal lens which could be by autofocus maintain its focus at the surface of the recording media, storage media. And what happens is when we apply a laser light for a pulse such as 1, then we cause a pit in the aluminum coating of the storage media on the order of a micron diameter. And then when we, and it could be a 1 and 0, and then when we play it back, the reflectivity of this surface is very high. So the sensing device is going to read the reflected area when the beam is hitting the surface, but it's not going to read the reflected beam when it hits the pit. So that's the principle of optical recording. LED displays are very common. We see here an example of displays. This is a 1-inch LCD screen, touch screen, a thin film. And over here we see the principle. We have the light emitting diodes at the intersection of the rows and columns over here. And the columns are the anodes. All the columns are connected to the same anodes, and all the rows are connected to the same cathode. And in order to activate a certain LED, we have to apply the voltage, 5 volts or 3.5 volts, to the anode, and then ground the cathode, and then this LED is going to be displayed. And we have a group of them. We could construct various features. The measuring systems, there are many of them. This shows an example of one of them by Monit. There are a large number of applications and industries which are using it. There are sensors, gateways, softwares, and accessories involved with measuring systems, and the communication between them is a subject of a different lecture. But what we see here that the sensors, wood temperature over here, or water detection, will transmit the data through wireless communication to a gateway, and the gateway will then, using circuitry with logic circuits, as we seen, transmit that into the monitoring and alert system, and possibly to a cloud, and may also transmit it back to an actuator at the recorded area. This completes our presentation, and we continue with more on actuators in upcoming lessons. Thank you.